Most of them are just like even the ones on my tractor.
It's our last one, chapter 5. That's a good thing, isn't it?
That's not a good thing. That's not means there's a test coming in.
That's right.
No.
You'll be fine. You guys are doing well with this chapter. So,
Okay, kids, we'll get rolling here this morning. So I've got to record here about the first couple of pages, or first page of this at least here. And guys, a lot of stuff that we've done in the past and what we've done so far in this chapter are going to kind of come together in this section. This is titled Modeling with Logarithmic and Exponential Functions. So nothing different here. You've been looking at a lot of logarithms and looking at a lot of exponentials throughout the whole chapter, so that won't be anything that's new. Okay? But what we are trying to answer is this: how can you recognize what's known as a polynomial? We've done polynomials, exponential, and logarithmic models. And honestly, all the things that we've done in the past, you know how we've always talked about how stuff move up, right, left, down. We've done that over and over and over. Okay? We've done some modeling. Some of the things that's going to come into this is regression with technology. We're going to be putting some stuff in with technology to come up with functions. So honestly, nothing really new here. It's just going to be something that we've done in the past applied to logarithms and exponentials. So our goals today, we want to classify some data sets. Are they logarithmic? Are they exponential? Or are they a polynomial of some sort? We're going to write some exponential functions today. I'll show you how to do that. And then we're going to use Desmos to find some exponential and logarithmic functions. So you may want to have Desmos out. If you don't, I'll be showing it up here today. That's fine. However you want that to work. Okay? So some things we need to recall, kids. Finite differences. Finite differences. You remember talking about that? Okay, let's recall this. It says data with equally spaced inputs to determine what type of polynomial function can be used to model the data. Let me give you a data set up here. Maybe make this set right up here. Let's make an XY table up here. Remind you what a finite difference is. Oh, I don't want that. I want my answers to be the following. I'm sorry, 1 through 5.
Give you a pencil.
No.
Yes.
I like it.
No. I don't care. Use my pen.
All right, come on.
Give me a pencil.
Now, I have you throw that table up in there quickly just to give you an example of what finite differences is. Okay, way back when we talked about polynomials, we talked about functions that had certain degrees, like a third degree or a fourth degree or a fifth degree function. Remember talking about degrees of functions? Okay, so finite differences are like this. Finite differences usually represent what type of function here, according to your definition? Okay, the way you look at it is this. Kids, what's the difference? Okay, first of all, are all the x's equally spaced? In other words, 1 to 2, 2 to 3? Okay, you got to have x values be equally spaced. What's the difference from 6 to 3? What's the difference from 11 to 6? How about 18 to 11? What is that? 27 and 18. Okay, now is that first row of differences exactly the same, or is there changing in that? Okay, so what we do is we look at a second row of finite differences, and we say this, kids. What's 5 minus 3? 7 minus 5. 9 minus 7. What do you most about the differences in the second row? Okay, and since the differences are the same in the second row, we say this could be modeled by what degree of a function? Degree 2. Okay, so since row 2 is the same, I'm going to say on the right, this models what degree? This models a second degree function. Guys, when I talk about second degree function like x to the second, like this, that is what type of a function up here? Polynomial, isn't it? Okay, it's going to be polynomial because we would have a second degree function, meaning our exponent is always going to be a 2 up there. Okay? Now, that's common differences. All right? Now, finite differences usually represent what type of a function again, kids? Okay, for a geometric sequence or geometric series, the common ratio is the ratio of the term to the previous term. This ratio is usually indicated by the variable r. I'll tell you this right here, common ratios are very different than common differences, but common ratios usually represent exponential functions. So let me give you a table. Let's go 1, 2, 3, 4, and 5 for my x's. And then for the y's, guys, let's go, I don't know, let's start with, I don't know, 1. And then let's go to 2. And let's go to 4. And let's go to 8. And let's go to 16. Okay. I want to ask a question right here. Could I do finite differences in this, kids? I could. I get 1, I get 2, I get 4, I get 8, and you're going to run into a mess with this, okay? But in the y's, in terms of the y's, do you guys see the pattern from one value to the previous value? Instead of doing differences which means subtract, look at common ratios. What is 2 divided by 1, kids? Okay, so I'm going to put a 2 and I'm going to circle it so I know we're doing ratios. What's 4 divided by 2? Instead of doing like subtracting up top here, which was common differences, we're doing division to see if anything happens here. 8 divided by 4 was 2. How about 16 divided by 8? Okay. This here is not a common difference, but this is rather called a common what? Ratio. Okay, to go from 1 to 2, what do you multiply by? To multiply to 2 and to 4, you multiply by, okay. So you're kind of looking for patterns right there, all right? And if you don't have finite differences, which represents typically polynomial functions, common ratios are something else to look for today. And common ratios are going to usually represent what type of function? Exponentials. Okay? Exponentials. All right? Okay, another thing we need to recall is point-slope form. Point-slope form is for linear functions. Okay, this is the formula. Y minus y1 equals m times x minus x1. We can write an equation for any line if we know a point and what else? Okay, pick a point, kids. 2, 7. Give me a good slope value, kids.
2.
All right. If I said, hey, you have a line with a slope of 2, and it passes through the point 2, 7, could you put an equation in point slope form for me? Yeah. Let's do that right now, okay? We're going to go with y and x are my variables. So y minus y1. In other words, y minus the y value of the point. What is the y value of your point? Y minus 7 would equal your slope m. Okay. Now, could I manipulate this a little bit? Could I, in other words, expand on the right and distribute on the right and get y alone if I wanted to? It'd be pretty easy to do, wouldn't it? Okay. All right, so as far as vocabulary goes for today, okay, do you understand the difference between finite differences and common ratios? Finite differences help you determine what type of a function. You're always subtracting. Sometimes you get the same value in row 1. Did we get the same values in row 1? Where did that finite differences become the same? Row 2, which meant it was a what degree polynomial? Okay. And if subtracting doesn't help you find some kind of a pattern, then we're looking for not common differences, but common what? Ratio. Okay. One value divided by the previous value. All right. Okay. So let's take a look at the two tables down below here, kids. I want to know if classifying data sets is either exponential or if it's polynomial here. Okay. Now, you want me to make life a little easier for you on this? Okay. You're typically checking between either exponential or what first? I'm telling you which is which up here in the notes, right? Okay.
Yeah.
But if they say, here's a table, determine if it's exponential or polynomial, here's your hint. Always check for exponentials first. Okay? Either you're going to have a common ratio or you aren't. Okay? So check this out, kids. Somebody take 81. Well, I should back up here. Are all the x values equally spaced to begin with? Okay, that's a key thing. The x values have to be equally spaced. Do this for me. In your calculator, do 81 divide 243. Point 3 repeating? Okay. 27 divide 81. Point 3 repeating again. It's going to reduce to 1/3, right? 9 over 27. Won't 9 over 27 reduce to 1/3 again, kids? Yep. Guys, I say check exponentials, and even though I told you this is an exponential example right here, always check exponentials first using division, because either all these values are going to be the same or they're going to be very what? Won't they be either the same or different if I'm dividing? Okay? If they're all the same, then you know you have what kind of a table already, kids. Okay, so check your division part first. All right? What's 1 divided by 3? Okay, so I'm going to write down here, common ratio. By the way, is this showing growth or decay? Yeah, values are going down. Well, the value, common ratio is 0.3 repeating, which indicates an exponential function. And we'll get to start writing those here in a second. Okay? But when you have a common ratio of all those y values, if it's the same and it happens the first time and it says, oh, common ratio is this is going to typically indicate some kind of an exponential function. Now, whether that's growth or decay, you'll have to look further into that. Okay? Now, what type of example am I suggesting on the right? Polynomial. That would not deal with common ratios, but rather that would deal with common what? Not common ratios, but common differences. So we're going to do some subtracting, right? Kids, what's 5 minus 13? Negative 8, right? Then 13 minus 5? 37 minus 13 is what, 24? 77 minus 37, that's an easy one. 133 minus 77, I think, is 56? Is that a linear function? Why not? Row 1 difference is the same or different? Different. Okay, well, let's check the next one. How about 8 minus negative 18, kids? I'm sorry, 8 minus negative 8. Negative 18. 16. What's 24 minus 8? 16. McGurd. What's 40 minus 24? 16. I'll bet you 56 minus 40 might be about, how much?
16. 17.
Whoa. 16. What happened there in that second row of finite differences or common differences, kids?
All the same.
All the same. So is this going to be exponential or is this going to be polynomial?
Polynomial.
Okay, so I'm going to say right here, common difference, meaning 16, common difference in which row, kids?
Second.
Common difference in row 2 indicates that this is what degree?
Second.
A second degree polynomial. Now, kids, like I said,
I told you what each one would be up here before we even started, but if they say here's a table, determine if it's exponential or polynomial, what should you always check first? Exponential, because this ratio, when you divide one value by the previous value and then do this throughout the rest of the table, it's either going to be the same or it isn't. And if it isn't, then you need to go in and check for what then? Go check for common differences then after that, okay? All right, friends, how about this? Are we good on first page right now? Any questions first page right now? Okay, let me roll ahead to page 2. And I think I'm going to stop recording right there because I think I've got this one. Give me 1 second here, kids, to do something.